To write mostly on this and we'll see what happens. Okay, so we were talking about Markov networks and the representation of the Markov networks, and mostly what I'm going to do is sort of complete the discussion on connecting up the inference part and the learning part, and then hopefully since actually I might have more time, and so I might also bring in generalization of Markov networks to relational Markov networks. And it turns out you can also do generalization to relational Bayes networks. We just didn't talk about it in this class. So hopefully I'll just bring up some aspects of that too. So anyway, for the as we mentioned last time, the point about the okay. So this is the example that we looked at last time, and there's a lot of stuff here. But essentially, once you have a Markov network, then once you decide the topology of the network, okay, then basically you need to provide some information about how the nodes configurations are connected to each other. Okay, and again, we are looking at discrete variables. So we are actually in this case looking at Boolean variables. And then so these basically, the way you tell how they are connected to each other is basically saying for every clique you provide a clique of which is a subgraph of this graph that's a clique. You provide the affinities for individual configurations. Okay, so for example, AB is a clique. And for AB, you're saying A and B will be 0 has 30 affinity, A and A0, B1 has 5 affinity, A1, B0, 1 affinity, A1, B1, 10 affinity. Okay, it's and I mentioned a lot, we spent a lot of time last time talking about the fact that they have no probabilistic semantics whatsoever. They are not marginals, they are not conditionals, they're just factors. Okay, and they basically, in fact, they don't even have any probability numbers, right? You can put any numbers there. All you need to do is the affinity is all positive, okay? And then what you can then do is if you basically multiply the factors, and I mentioned what factor multiplication is, it's essentially a join operation over the factors, okay? Then you will get the full unnormalized distribution, and from that you can get the full normalized distribution, okay? So again, the whole point of any graphical model is that suppose you happen to know this is the distribution. Could you have figured out a network which exactly captures the distribution? Okay, that's the reverse thing. Normally we just basically go ahead and go from here and make these numbers and so on. But like an expressiveness question is, if you have a particular probability distribution over A, B, C, D, could it have been represented in in a particular, is there a network, a Markov network in which it could be represented? Okay, so it turns out that the answer for that is no. In fact, there are probability distributions which cannot be exactly represented as Markov networks, and in fact, there are probability distributions which cannot be exactly represented as Bayes networks either, because for it to be exact, it must be the case that all the conditional independence that hold here must hold here and vice versa. Okay, notice that if I were to give you a distribution like this, you can tell what is independent of what given what. You realize that, right? Because if I give you the entire distribution, then if I ask you the question, is A independent of B given C? Okay, then yeah, you can do that, because basically you can compute the probability of AB given C, and then probability of A given C and probability of B given C from this, just by direct marginalization, multiply the last two and see if it is equal to the first one. If so, the conditionality, that independence holds, otherwise it doesn't. You see what I'm saying? So anyway, so then basically this tells you that given the network, this tells you how to give the distribution. And I also basically pointed out that we also pointed out that the way to parameterize this is in terms of the potentials over the cliques. Okay, and one interesting question is that this is basically this question I'm asking, that if I give you this and this, there is a consistent distribution. That's one direction. The other direction is, if I give you this, could you have come up with a Markov network? And I was sort of saying that it's not possible, because there could be cases where exact conditional independences cannot hold. Okay. However, you can. However, there is this Hammersley-Clifford theorem, which we won't get into, that basically says the maximum you can say, basically that the family of distributions defined by the conditional independent semantics on the graph. Okay, so what we are saying is, for the set of distributions which happen to have the same conditional independences as a particular given graph, it turns out that there is a way of finding the node clique potentials, so that you can then make the distribution be exact. Do you see what I'm saying? I mean, in the sense, in making the distribution be the same as this, you need to have two parts. One is the conditional independences, the second is the numbers. And I'm saying, if the conditional independences are already the same, then you will always be able to find clique potentials such that the numbers will work out to be the same.
I mean, clique potentials can be scaled, right, and still get the same.
Yeah, exactly. Yeah. But all I'm saying is there a particular, I mean, this is an existential proof, that's also, can you find a set of clique potentials? I'm not saying there is a unique one. I'm saying there is one, that's all. Okay? And that point about scaling is an important one, because essentially we are normalizing everything in the end anyway. Okay, so that's this big, you have to keep this in mind. And here is another example, just to give you one more example on Markov networks. So this one essentially is saying smoking, cancer, asthma, and cough. Okay, and and these are all Boolean variables, and I essentially said this is the connection. Okay, and notice, by the way, that already you should remember that the arrows in the Bayes networks are not causality. You should get that for sure. It's like you can get by with sort of an assumption that they are causality, but really they have no connection to causality. I mean, you can given a set of variables and a causal theory of what variables value causes what other variables value, I can invert it and still get a Bayes network. Okay, so Bayes network has no actual connection to causality. The directions have no connection to causality. Okay, and similarly here, of course, basically those edges are really about talking about correlations between variables and what kind of conditional independence assertions will hold. Okay, and as we mentioned last time, in this particular case, I can ask questions such as, is smoking independent of cough given cancer? Yes or no? Is smoking independent of cough given cancer? Yeah, because if I remove cancer, there is no way of going from smoking to cough. Right? Okay. How about, is smoking independent of cough given asthma? No. That's basically the point of the conditional independence assertions. Okay. And so now, having asked these questions, then I put the links. Okay, the way you can ask yourself, how did I come up with this particular topology? In some sense, that's a logical connections. I mean, this is about the conditional independences that you think hold between the variables. Okay, if in fact you think smoking is not independent of smoking is not independent of cough even given cancer. For example, in the domain you're looking at, let's say, I don't know, what else? Maybe smoking can cause cough not just through cancer, but through something else. You see what I'm saying? If you believe that, then essentially you need to put that particular variable also into the picture. Okay, and then just removing the cancer won't make them independent. You need to remove both of them. Okay, and then again, given this particular thing, I can again talk about cliques. So in this particular case, there is a one clique here, there's a two clique here, and there's a three clique here. Okay, so here is a made up potential on the 2-click, and I can also make up a potential on cancel as Markov. Okay, and once again, just like in Bayes networks, the numbers you put in the the actual numbers you put in the conditional probability tables of Bayes networks doesn't matter in as much as keeping the network consistent. Whatever numbers you put, they would correspond to a consistent joint distribution. That may not be the one you are looking for, but that they will correspond to a consistent joint distribution. Similarly here too, whatever numbers you put here, it will correspond to a consistent joint distribution. The trick, of course, is they correspond to the one that you have in mind. Okay, presumably, just as Bayes networks, you ask experts, what do you think is the probability that A will be true given B and C are true? And the two ways you can get these numbers in any of these probabilistic networks is ask the expert, okay, what do you think is the probability, and assess the probability that way, or learn from data. Okay, and we did the learn from data part already for Bayes networks, and we'll sort of do the learn from data part here too. But ask the expert part is always a possibility. Now the only tricky thing here is when you ask the expert here, there is no probabilistic semantics. So to the extent we believe that humans, experts have very clear understanding of what probabilities mean, they don't know what these numbers are supposed to mean. And the scaling issue comes front and center, because at least in the case of probability, the scale is decided between 0 and 1. Okay, fine. Anyway, so then that's another example. And once again, the probability distribution is multiplication of these factors divided by, of course, the summed quantity. Okay, so that's this one is called the partition function. So what this is doing, in essence, is it's basically computing the entire joint distribution, and it's adding up the joint distribution. So if you're, for example, asking what's the probability of x being equal to true, okay, then you are computing probability of x being equal to true marginal on the unnormalized distribution, and you're dividing it by the sum of probability x being equal to true and probability x being equal to false. That's where this summation is coming, right? Okay, that's basically what we're doing. Okay, one other thing that makes Markov networks, this is basically the background of Markov networks. One other thing that makes it interesting is actually, let me see whether I should want to do this first. Okay, let me just do this first. Okay. I missed one slide. I want to show you. Okay, yeah, expressive power. I want to show this and go back again to the log models. Okay, so one thing that I've sort of been saying is that Bayes networks and Markov networks, neither of them are enough to capture all possible conditional independence assertions in a given graph. Okay, and to do that, all I need to do is give a counterexample, right? I mean, normally to say that something is complete, I need to provide an inductive argument. To say that something is not complete, I need to provide one example. That's enough. Okay. So here is the canonical examples of Bayes, both a Markov network and a Bayes network, such that if your distribution is exactly representable by this Markov network, and that means the conditional independence that hold in this distribution hold in your real distribution, and vice versa. Did you see what I'm saying? Okay. Then it turns out that distribution. So you have a real distribution, P star. P star is exactly representable by this. Then you can argue that P star cannot be exactly representable by any Bayes network configuration. Okay. Because essentially no directed model on 4 variables. There are only so many directed models on 4 variables, right? No directed model on 4 variables can represent exactly these 2 independence assertions, and no more and no less. Okay, so that means x must be independent of y given w and z, W must be independent of Z given X and Y. Those are the only independences that hold here, right? Okay, so try writing, the networks on 4 variables on Bayes network, and you will see that you will either do a little more than required or a little less than required, never exactly this. Okay, and that brings up the question, if you can do little more or little less, which would you rather do? We talked about this. So if your real distribution, only has these 2 conditional independences. So I can give you one Bayes network which does these 2 plus 1 more. Another Bayes network which only does 1 of these and no more. Which one would you rather use? Neither of them are exact. Which one would you rather use? Obviously, there is a trade-off. Okay, the one which represents these 2 plus 1 more is making more assumptions about independences that actually don't hold in the real world. Okay, so it will be computationally easy to do inference with, but its answers are likely to be inaccurate. People do it all the time. Naive Bayes classifier makes humongous number of assumptions about the distribution, real distribution, but it still winds up being useful. Okay, but that naive Bayes classifier is going to give wrong answers. Some of the time those wrong answers wind up being the right enough for us. Okay, and similarly the other case where you only represent one of these and no more and no less, that such a Bayes network is going to essentially be accurate. Whatever assertions it will make about the probabilities will still be correct. It's just that it will be less efficient computationally, because the more independences are holding in the distribution than you are actually putting in your model. Yes?
So what parameters decide that we should go with these two, the more descriptive one or the less descriptive one?
What do you mean? I didn't understand.
So if I have to make a choice, so how do I make a choice between these two?
That's what I said. it depends on, are you trying to be ensuring accuracy or computational efficiency? If you want, so whenever this question, if you want to remember the answer to this question, think of, do you want to use a naive Bayes classifier on 5 variables, okay, or a fully connected Bayes network on 5 variables? Do you see what I'm saying? Okay, I can tell you for sure that a fully connected Bayes network is likely to capture a lot more real distributions on 5 variables, and the naive Bayes classifier will do. But it will also have much higher inference cost, and it will also have much higher learning cost. The naive Bayes classifier, on the other hand, will have much lower inference cost, much lower learning cost. Most of the time would be wrong. So people actually have to write a paper on the unreasonable effectiveness of naive Bayes classifiers. In fact, one of the most cited papers by this guy called Pedro Domingos is, why does a naive Bayes classifier wind up working so well? It's an interesting question. Okay, you can ask yourself the same thing. Linearity assumption. Why does linearity assumption work so well in the world? We make linearity assumption to mostly make our life simple. It's not that the world is made up of linear processes. But however, an assumption that we made to make our life simple winds up being quite effective. Why? Okay, that's an interesting question. Okay, so it turns out, by the way, for the naive Bayes classifier, an interesting argument that Domingos makes is you need to differentiate between. So much of the time when you're doing naive Bayes classifiers, suppose you have some particular real distribution P star. Okay, over some variables A, B, C, D, right? In fact, class and A, B, C, D. Since we are talking about naive Bayes classifier, you have typically a class label and then the attributes A, B, C, D. Okay, now the interesting thing is the true distribution will give exact probabilities for class given a particular values over A, B, C, D. And the naive Bayes classifier also estimates these. These numbers can be wildly inaccurate from the naive Bayes classifier side compared to the real distribution. So for example, suppose there are only 2 classes, C1 and C2, I mean, C equal to true or C equal to, I mean, C equal to class 1 or class 2. Okay, the true distribution for a given configuration of ABCD, maybe the true distribution of conditional probability C given ABCD is 0.99 and 0.01. Suppose you did a naive-Bayes classifier on CABC, okay, at the class and ABCD, okay, that may have come up with 0.51, 0.49. These distributions are like night and day different, right? Okay, and yet if all you're doing is using this distribution, pick the maximum, the one with the higher probability and say that is the class, you'll be correct whether you use this or that. Do you understand what I'm saying? So the point in the naive-Bayes classifier is at least that even though the reality, in reality, naive-Bayes classifier assumption is actually a pretty lousy assumption. It's particularly lousy if you're talking about approximating the entire distribution. But if you are only using it to decide the class label, you can be right more often than you might be thinking pessimistically. Does it make sense? So for example, you could be wrong, like 0.51, 0.49, 0.6, 0.4, 0.7, 0.3, all of them are different from the real distribution. And yet they'll all give the exact same decision. Okay, so that winds up being an interesting point to keep in mind. But this is like a big digression we made from here into, when you know that certain conditional dependencies don't hold, should you make that, when you know that you cannot exactly capture the conditional dependence in the real distribution, would you rather go for fewer or more? You go for more if you want to make life simple for you. You go for fewer if you want to increase the accuracy of the estimation. Okay, fine. So, but now coming back to our original point, these particular two conditional independence assertions, and no more or no less, cannot be captured by any 4-variable Bayes network. So there I gave you a counterexample saying Bayes network. So that basically shows Bayes networks are not general enough. Okay, to now then say that Markov networks are not general enough, I will give you even a simpler example. If you have x, y, z such that x and y both have a directed edge to z, okay, that basically, the crazy thing about this is, given nothing, x is independent of y. Given something, x no longer is independent of y. It's actually, this is the craziest part about Bayes networks. Okay, in general, conditional independences increase monotonically as evidence increases. Do you see what I'm saying? In Markov networks, x is not independent of y given nothing. It's still not independent of y given w alone. And it becomes independent of y given w as well as z. So as the evidence increases monotonically, the independence increases. Right? That is what common sense, that sort of looks almost like that's the normal thing that should happen. The neat thing about Bayes networks is actually there are cases where when the evidence increases, the independences reduce. Okay, now of course you might say then if you never have a real world distribution where such a thing happens, then why should I have something like this? But unfortunately we do have real world distributions because this captures what is called what? This beautiful structure captures what's called the explaining away. Okay, in the burglary earthquake alarm example, if nothing is known, burglary is independent of earthquake. If I told you alarm occurred, then you don't need both burglary and earthquake to occur. The moment, if you know that alarm is going off, and if I tell you burglary occurred, then the need for earthquake to occur has reduced. Because I already have a good explanation as to why the alarm occurred. You see what I'm saying? Okay, that is a common sense, we do this in common sense reasoning, plausible reasoning. And there is no way of capturing that sort of a independence here. It can be captured here. Okay, so this particularly, so essentially we are saying that there is no three variable Markov network such that it only captures this one independence relation. X is independent of Y, nothing more. You see what I'm saying? Because you might say, well, okay, why not this? X, Y, Z. Okay, right? If you do that, X is independent of Y, but also Y is independent of Z and all sorts of other things. You see what I'm saying? Okay, it turns out that you can try other Markov networks and it turns out they'll always do either more or less, not exactly just this. Okay, and it's almost required in this explaining away is required. So this sort of tells you why you would need both. A more interesting question is actually, if you have both, will you then be able to capture every possible kind of conditional independence that holds in a distribution? That answer is more complicated. I won't go into it. Okay. In fact, one of the interesting things, at least that you can tell, is that if you start from a Bayes network, so one of the interesting things is that you don't have to just have pure Markov network, pure Bayes network. You can have a network which looks like this. That's Markov Bayes network. If you think I'm making this up, you'll see that, as I mentioned in that collapse Gibbs sampling, write-up, which we'll hopefully get to by the end of the semester. When you do collapse Gibbs sampling in LDA, okay, LDA starts out as a pure Bayes network, which has a continuous variable in it. Now, one of the things you can do is you can remove a variable, compile it away. So when you remove that variable, so one of the things, so if I have a variable A, it's connected and it's basically, it's like this C and then C and D. Suppose you have a network like this, conditional, a Bayes network like that. Okay, now it turns out that I don't like A because A is continuous. I don't want to think about A. So I want to remove A from consideration. How do I remove it? When I remove A, essentially then B and C become connected. How do they get connected? They actually get connected undirectedly. Okay, so the interesting thing there is that then if I remove this, if I have a continuous variable and I don't want to deal with the continuous variable, I might remove it. In fact, again, in the beginning Bayes networks lecture, which you are supposed to have heard, I think I spent a lot of time saying, why might you introduce hidden nodes into a network? And oftentimes you introduce a hidden node into a network to increase sparsity. Sparsity both in terms of the edges and in terms of the size of the factors that you have to specify. Okay, and one of the things that will happen when you get to this, this sort of removing a node, it almost flies in the face of that intuition. Why would you want to remove a node? Well, it turns out that if I don't remove the node, then I need to do continuous inference. Okay, so I would actually remove it and then handle, basically handle the continuous variable as if it is just a background influence. Okay, so that basically tells you that, in fact, you can start with an Bayes network and what's called moralize it. This is basically, there's a beautiful name for this. This is called moralizing. And the moralizing, basically, when you remove that network, guy, then you would wind up getting extra edges. And then that might be a mixed network. Okay, the interesting, so anyway, so that's the point. So you need both of these, and sometimes you need actually both at the same time. One thing, of course, is there is burglary and earthquake. That is a great example here. One issue is, where are Markov networks used widely? Not surprisingly, if you think of an image with pixels, a value of a pixel, an intensity of that pixel depends somehow on the neighbor's intensity. You see what I'm saying? Okay, and there won't be any explaining away phenomenon. Typically, it's very hard to talk about pixels saying, oh, I don't need to be, up anymore because this other guy is up. You see what I'm saying? Okay, so in fact, Markov networks, they've also been called Markov random fields, and they were originally used a whole lot, both in statistical physics and vision, computer vision. Okay, and they capture, and as I said, there are beautiful properties of Markov networks because the neighborhood, is, so for example, one of the interesting things is, since we are talking about this, what happens to the Markov blanket? What's the Markov blanket of a node in the Markov network? Don't say parents. There are no parents in Markov networks. Everybody is created equal in Markov networks. There are no parents.
It's 2 steps away.
What? Just neighbors. Your neighbors are your blanket. That's very natural, right? That's very natural. Whereas in the case of Bayes network, it's much more complicated. It's your parents, your descendants, that is neighbors, but then your parents' other children. I'm sorry, no, your descendants' other parents. That doesn't make any sense. Where did that come from? Do you see what I'm saying? Okay. So in a way, Markov blanket for Bayes nets is less natural than Markov blanket for Markov nets. Natural, I don't know. Especially from an image point of view, it's quite natural that an image, its intensity is directly dependent on its neighbor's intensity. If it's like you're looking at a grid, then essentially an image's intensity is just dependent on the cells surrounding it. That's it. And to the extent other cells have any connection to this, if I know the neighbor's connection, then that would, if I know the neighbor's values, then I don't need to, the influence from the other guys has to be mediated through the neighbors. Okay, so Markov blanket for Markov network is just the neighbors. Markov blanket for Bayes network is more complicated. Right, okay. So I'm actually, okay, so there's actually the Markov blanket. So, yeah, there you go. So your network looks, crazy networks, completely connected networks look like this. That's for the images, right? And this guy's neighbors are these 4. Okay. Whereas for the Bayes network, this guy's neighbors are the 2 descendants, the 2 parents, and the other parents of the descendants. Okay. Now I'll come back to this in a second, but let me go and show one more point. Let's see, where are we? Okay. So there is an interesting thing that people do, which is knowing that all the click potentials are positive, and you have to multiply the potentials to get the other probabilities. Since multiplication is not as much fun as addition, you just represent click potentials in terms of their logs. Okay, right? Because a number 5 can be represented as what? E power log 5. Right? Okay, so then I will think of potentials only in terms of the log form, and the exponentiation is expected. Then when I multiply the logs to logs, then I'm basically adding up the logs. When I'm multiplying the potentials, I'm adding up the logs. Okay, this is something that is sort of done pretty widely. People just, after saying click potentials are multiplied, they'll right away go into the assumption that all click potentials are represented in this log form. Okay, and it's just sort of assumed that that's the case. So then basically, so phi 1 AB, phi 2 BC, phi 2, phi 3 CD, phi 4 DA. This was my original example. So then when you represent these in terms of e power log 30, so this is log 30. Okay, now the only difference is actually they will write this with a minus in front. So you'll put a minus here so that the minus will cancel out. So you write the potential as e power minus Wi Fi, where Wi is the weight and Fi is a kind of a feature which is sort of that will hold yes for a configuration and or not hold for a configuration. So think of a feature as a Boolean function over, a feature as a function over the actual values of the random variables. Okay, I'll get to that in a second again. Okay, so so in this particular case, I will think of phi d as e power minus form, e power minus epsilon form, and then where epsilon d is just nothing but minus of ln of this d. Okay, and then so you have these as your potentials, and when you do multiplication, you just add those numbers up. Okay. This is something that's just done. Now, so you can think of factors as basically functions over domains anyway, right? Basically, they are saying the domain of the factor is AB, and it's sort of giving a value based on, if A is 0, B is 0, this is a number. A is 0, B is 1, this is a number, and so on. It's a function over these particular configurations. So one way of compactly representing functions, obviously, if you have, how many, by the way, if these are Boolean variables, how many different, real valued functions, of course, they're large number, but even Boolean functions, they're large, So that means even if I'm only considering functions that are ones and zeros here, how many Boolean functions are there on n variables? What? How many Boolean functions are there in on n variables? 2 power n functions? If you have n variables, right? Okay, to write the Boolean function on that. So if you have n variables, so this is a1 to an, and then I have to say this is a true, true, false, 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 false. Then one more thing, one more thing, one more thing. That's the various combinations that a1 to an can take. A1 to an can take, right? And for each of the combinations, I need to say true or false, or 1 or 0. Okay? And how many rows are here? What? No, come on, guys. How many rows are there when you have Boolean variables a1 to an? There are 2 power n rows. There are 2 power n configurations. Okay, so I now have 2 power n rows, 2 power n slots that I can independently put ones and zeros. So how many different ways can I do it? 2 power n. The number of Boolean, this just has to kind of go in, basically this is what makes learning hard. Okay, even if I tell you that the concept I'm trying to teach you is a Boolean function, there are 2 power n Boolean functions. The 2 power n Boolean functions. For 10 variables, that works out to be some, I have this, something like 186 trillion or something. It's 2 power 10 or 2 power 1024. Okay. And one of the great rules of learning, actually again this is something that we're going out of this particular lecture, is the PAC learning theory, the probably approximately correct learning theory says that you need, the complexity of learning is in terms of the number of examples you need to learn the concept correctly. Okay. And if the concept I'm trying to teach you has 2 power n possibilities, then it turns out that I need to give you at least log of the number of possibilities as the examples. Okay, that's basically the pack learning theory. And so then what happens is, when you are trying to learn a Boolean function, you need 2 power n examples. So Boolean function learning is considered hard, not because it takes exponential time, but because it takes exponential number of examples. Learning is hard when the number of examples required to learn the idea is hard. It takes more time. Okay, the slow versus fast learners might spend more time processing each example, but that's not the issue we are interested in. We're really interested in how many examples do I need to give you, labeled examples do I need to give you. The reason Boolean function learning is hard is because there are 2 power n of them. Log of 2 power n is 2 power n. Conjunctive function learning is easier. If I told you that there is a function a1 to an, it turns out this function can be compactly represented as a conjunction over a1 to an, some conjunction over a1 to an. How many such conjunctions can I write? Because in the conjunction, the variable can occur positively, variable can occur negatively, or variable may not occur at all. So for each variable, I have 3 possibilities. So the total number of conjunctions over n variables is 3 power n. 3 power n looks bad, but man, it's like something to celebrate compared to 2 power n. More importantly, what is log of 3 power n? That's polynomial in n. Conjunctive learning is considered easy to do because the number of conjunctions is only exponential. So the number of examples you need is only polynomial in the number of features. This is basically the theory of learning, learnability. Of course, this stuff, what I just said right now, is great for Boolean, the Boolean attribute values. But there are ways of expanding this to continuous values. Okay, but the bigger point is that whenever you have, whenever I'm saying that I'm teaching you a Boolean function, there's just too little a bias because there are too many, functions. Then I will say, well, it turns out that not all combinations over a1 to an has to be considered. When I said conjunctions, I'm telling you the only combinations you have to consider are conjunctions. The real function is only a conjunctive function. And similarly, I can say the real function is in terms of some features over these variables. A feature basically is a smaller Boolean function. Okay, and then the weight would then basically tell you, so if this is true, then you multiply it by some weight, plus then you multiply another feature by another weight, and then you will get the affinity. So instead of writing a single affinity number like 100, you're saying the affinity that I have is in terms of these features. Now for machine learning people, features are like, you do this all the time. These are ways of introducing features over variables and then writing the entire description in terms of features. All this stuff, by the way, is syntactic sugaring. In the sense that really the first principles idea of Markov networks is that you wind up, giving affinities over these. Okay, but when you read something about Markov networks, if you read anything about Markov networks, they'll talk about features. In fact, the most popular thing about Markov networks outside of vision is conditional random fields, which wind up being Markov networks that are discriminatively trained. And to talk about that, we will have to wait until next week when I'll tell, if you don't already know the difference between generative versus discriminative models. It's a question, it turns out that, Markov networks are easier to train discriminatively. And then, people use them for conditional random fields, for segmentation tasks, for extraction tasks, and so on. Okay, and if you look at any paper on conditional random fields, it looks at this kind of a form for the distribution, but will also have features. It basically rather than write it this way, it will write it this way. The overall distribution is essentially exponent of a weighted summation of features, where each feature is essentially a Boolean function and a subset of the variables. So, for example, the feature fi, in this case, is this my feature is smoking cancer feature. The smoking cancer feature will be 1 if not smoking or cancer, and 0 otherwise. So, given a configuration, you can tell whether this feature is 1 or 0. Right? Okay? And then I'm telling you that if that feature is 1, then you multiply, and basically that feature is being multiplied by a weight wi, and I'm wi in this part, w1 in this particular case is 1.5. Okay, since now, so previously, we started from the number of free parameters here is actually all of these are free parameters. They all had to be learned. Right, here also all of these are free parameters, all had to be learned. But now you are saying each of these are made from only 15 features. Right, because that's what this thing is saying. It's not, it's made directly from the features. So what are the free parameters then? What do you need to learn in this case? Weights. What does this remind you of from a Bayes network side? If you have a normal CPT, that is an extensional CPT, you need to learn every number in that CPT as part of Bayes network. If on the other hand, I have a parameterized CPT, either a Poisson distribution or a noisy R distribution or a Gaussian distribution, then I just need to find the parameters for that distribution, and then that will then essentially fill up the rest of the numbers. Do you see what I'm saying? So getting the features in is the way of saying, these numbers are all not independent. I have a parametric distribution, and I just need to figure out the weights for the parameter. If I said, the entire CPT, this is a continuous CPT, and it turns out, it's basically filled by a conditional Gaussian, then all you need to learn is the mean and the variance of that Gaussian, even though there are infinite number of numbers I need. Right? And similarly, here, even though there are exponential number of numbers I need to know, okay, I'm just saying they're all parametrically, they are basically going to be representable only in terms of these features. This is the game that feature engineers play. This is a backdoor way of putting more knowledge into the learning task than there was originally. Do you see what I'm saying? I mean, if my features are only conjunctions, let's say, okay, then essentially I'm saying I'm sort of learning a conjunctive function. Okay. Okay, so but this is useful to know. This is not, it's not lossy. You can always say a feature fi would basically, you can write as many features as there are combinations, for example. Okay, I can just say I have a feature on, in this case there are 4 variables. I can have features that are defined on all 4 variables, and the feature 1 will be true if this is true, 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 true. Feature 2 and will be 0 everywhere else. Okay, feature true will be true when this is true, 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 false, and be 0 everywhere else. Then I will have an exponential summation here. But the weights for those features would be exactly the independent numbers in each of these places. Okay? So that's basically worth remembering, that Markov networks are typically written up in this, distribution form. Okay, parameterized distribution form. This parameterized distribution is also called the Gibbs distribution. Gibbs is all over the place in statistics. In fact, one interesting thing to keep in mind is Gibbs was the first American mathematician who is of any reputation. Before that, all reputed mathematicians were, from Europe. Okay, Gibbs was in Yale, and essentially he dabbled in lots of things and made huge impact in everything, actually. Okay, so we talk about Gibbs sampling, we talk about Gibbs distribution, we talk about all sorts of other things too. Okay. Anyway, let me just show you one more thing. Oh, where did they go with that? Yeah, actually, I'm sorry. It's not. I think they're called Boltzmann distributions. I made a mistake. These are called Boltzmann distributions. It was much older than that. It's not. Okay. So you're writing the distribution in this exponential format, and they're called Boltzmann distributions. And the reason there is interest in that way of writing it is physicists, use this in thermodynamics, statistical physics. Okay, that's another place where the entire Markov random fields came from physics, actually. And there is a paper by Gelman and Gelman, I believe. It has some obscene number of citations, 20,000 citations or something. And they are basically physicists who one day said, hey, this stuff that we do for a living can be used by all these vision people. And they wrote up, Markov random fields applications to vision. And that's when it sort of crossed over into computer science side. Okay. So anyway, it turns out that what we are putting here, we are thinking in terms of features and weights, but this minus h is also they have other interpretations in in physics called things like the free energy of the system and so on. I'm not even going to go into that. Okay. So for physicists, this sort of in this representation, those numbers have physical interpretation. Okay. So the last thing in terms of representation for Markov nets versus Bayes nets, this is something that you should understand. Okay, so here is Markov nets, here is Bayes nets. The form, both of them are product of potentials, product of factors. Okay, the potentials, the factors can be arbitrary factors. For Bayes nets, they have to be arbitrary. Okay, whereas for Bayes nets, you can actually write the factors as conditional probabilities. That was the whole deal that we did last time. Okay. Now, of course, it turns out for Markov networks, since they are undirected, cycles are allowed. For Bayes nets, because they are directed, cycles are not allowed. Okay. And there is a partition function or a normalization function. It exists for both. It just happens to be one for Bayes nets, and so you don't need to care about it. And you do need to care about it for Markov nets. And it turns out, you can see it in a minute, but, we'll see it in a minute, but you can almost see how that's going to kill all the happiness in learning Markov nets, Markov net weights, because the weights get entangled because of the partition function. Okay, and so even in the simplest case, Markov network learning, simplest case is complete data. Known topology complete data is the simplest case. In that case, for Bayes nets, MLE learning is just counts. It turns out that for Markov nets, it's not that. Okay, it turns out that essentially the objective function is complex enough that if you take partial derivatives, there is no closed form solution. So you actually have to do gradient descent. What's more, and again we'll see that in a minute, that what's more that gradient to compute, yeah, it's probably died, right? And then you can restart it again once in a while if you can. I think first, yeah, that's started now. Yeah, it's fine. Good. So the gradient when is the correct gradient for even the complete data Markov networks, complete data known topology Markov networks, winds up not only just counting up what is in the data, which we are good at doing, okay, but it also requires you to compute expectations over particular variables, particular counts. To do the expectation is a code word for inference. Okay, remember in EM, we had to do inference and learning, and inference and learning. I only had to do that when you have missing data, missing variables, incomplete data. It turns out you have to do this from the get go in the context of Markov networks. So one of the crazy things that happens is then people say, well, if life is so hard to optimize the real thing, let's optimize the non-real thing, which is easier to optimize. This is again zeroth order drunk searching for the keys under the light. Okay, the real objective function, because remember, gradient depends on the objective function. The real objective function will require the gradient, its gradient will wind up requiring you to do inference at every step. And inference can be quite costly. That's the hard part about EM, really. Okay, so then people say, well, we won't actually maximize likelihood at all, we will maximize pseudo likelihood, which turns out to be likelihood given only your neighbors. Okay, now there is no guarantee that if you maximize pseudo likelihood, you're maximizing likelihood. Okay, and however, people in vision just do pseudo likelihood maximization. Okay, now the levels of doing the wrong thing is just mind-boggling. We know that even if you do MLE, there is no guarantee that you got the right. You got the right numbers, because the right way to do it is at least map, if not Bayesian learning. So MLE is already, you do it because it's easy to do. And then even that becomes hard, so you do optimization of somebody else. This is what happens in Markov networks. And this is why people put it under the hood. No introductory AI course ever talks about Markov networks. But the tricky problem is that anytime you start doing anything, and that's okay, forget about it. Anytime you start doing anything a couple of steps long, you will wind up, this ugly cousin comes up, and it's actually, in fact, theoretically, it's more important to understand Markov networks than Bayes networks. In fact, if you notice this inference, that should blow your mind. Okay, inference, Markov networks, you can do Markov chain Monte Carlo, belief propagation, etc. And Bayes nets just convert to Markov networks. You see what I'm saying? The stuff that turns out to be just a special case. The real stuff is understanding how to do it in Markov networks. And if you understand how to do it in Markov networks, then Bayes networks is easy. Otherwise, everything looks as if you have to redo, all the inference algorithms, etc. Okay, that's why I thought it's worth, exposing you to it. At some point of time, you will need it. You can get by most of the time, but anyway. So a couple of things are very easy for Markov networks. Graph separation is the independence criterion, whereas for Bayes networks, you need d-separation, which is harder. Okay, and then so that's this stuff you need to understand. Okay, then two more things, and I think we are done for today. One, of course, is inference. Again, I barely did the full inference for Bayes nets, right? There are all sorts of exact inference algorithms, and then also approximate inference algorithms. Even in the case of approximate inference, there are two types of approximate inference algorithms. One is sampling based. The other is what are called variational inference methods, where they essentially they're deterministic methods, but they sort of assume a certain approximation to the posterior distribution form. Okay. In fact, I'll just throw this out, that understanding variational inference is like understanding the connection between reinforcement learning and MDPs. Okay. Sometimes you solve MDPs using reinforcement learning, which is a learning technique, even though you know the full model. Variation inference is sort of making a hypothesis about what the posterior looks like, which looks like a learning step, and then use that to actually do the inference. Okay, even though you know all the data, you know actually everything about this network, but doing full inference winds up being too costly, so you do variation inference. Okay, in the LDA paper, actually the only inference algorithm they talk about is variation inference. Typically, I'm not going to teach that here at all. I'm just saying that's one way of doing approximate inference. It's a deterministic approximate inference. It's kind of finding bounds. Okay. And in fact, if you keep this in mind, and if you look at even just the first page of the LDA variation inference part, you will see that they'll start from a plate model and they approximate the plate model by removing certain offending connections, and then say we'll assume that the distribution posterior for this will be close enough to the posterior we are actually trying to find. And that one I can find it much faster. Strange, okay, but that's the real thing about variation inference, okay. But the simplest thing that we can understand is basically the sampling-based approaches, which are actually the only ones that are widely used, okay. And the sampling-based approaches are like likelihood sampling, rejection sampling, and most importantly, Markov chain Monte Carlo. Okay, and I just want to show you that you can do Markov chain Monte Carlo on Markov networks. I only showed you how to do Markov chain Monte Carlo for base networks before. Remember, always the idea is you start with an entire configuration, you pick a node. Configuration means, okay, this is true, this is false, this is true, this is true, this is false. That's a state. Okay, then you pick a node, okay, and you resample it given its Markov blanket. And then you pick another node from that new sample, and then resample it again given its Markov blanket. And that will give you a Markov chain in the space of entire configurations. And it turns out that such a chain will have a stationary or steady state probability distribution. And once you reach the steady state distribution, then you can just take the number of times you are going. So after letting it go for a while, then so let's say you let MCMC's chain go for, let's say, first 10 million iterations, and then at that point you say it has settled now. So I assume that it's in the stationary distribution now. For the next 10,000 states, I remember which state came when. So the more probable states will come more often, less probable states will come less often. And you will essentially say the joint entry for that state really is just the number of times it showed up in that last 10,000 times. Extremely simple to do. But for that to actually be correct, asymptotically the same as the full distribution, you must make sure that, you need to basically prove that the MCMC chain actually has a steady state probability. And this is what I was saying, that if you have deterministic dependencies, MCMC chain will not have the good properties, because you may not be able to go from one state to another state if there is a deterministic dependency, because there is no ergodicity in the space of configurations. Okay, but if you have all of them are soft dependencies, all of them are probabilistic, then it does mix. There is a humongous amount of theory on Markov chains and the mixing time for a Markov chain. Some chains mix very fast. Some chains mix much slower. And the effectiveness of the MCMC depends on how fast the chain mixes. But it will work, as long as there are no deterministic dependencies, it will always work. And the per step complexity is very easy. The beautiful thing about any of these sort of sampling based approaches is it's easy to understand what to do. It's very hard to explain why it works. The math comes in explaining why it works, but what to do is very simple. Whereas for an exact inference algorithms, it's front and center. Even explaining what to do is quite hard. Okay. Anyway, so inference in Markov networks, essentially, you sample X given its neighbors, because Markov blanket happens to be just the neighbors. Okay, and that's basically what this one is showing. But let me show you an example that might be easier to understand. So here is a network. Here is a Markov network. Okay, and so suppose and remember again in MCMC, you're typically trying to infer the probability, let's say, of A given BCD. That means BCD are evidence. So when you resample, you don't resample the evidence variables. Those are clamped shut to the observed value. It's only the other guys you resample. And then taking the relative counts of those will give you essentially the conditional probability directly. Right? Okay. So in this case, essentially you are trying to, let's say, what I'm trying to compute is PD given not C. Probability that D is true given not C is true. Now, of course, you know that if I were to give you all the potentials on these clicks, you know how to compute that. You will then compute the entire joint and then marginalize it, and the right way until you get to get a PD on the top and D and not C in the bottom. I'm sorry. Now PD and not C in the top and P not C in the bottom. Right? Because A given, probability of A given B is nothing but probability A and B divided by probability of B. That's the definition of conditional probability. Okay, you can do that, but that's very complicated, unnecessarily hard way of doing it, because you're computing the entire distribution just to be able to answer this very simple question. So the question is, can I do it directly? And the idea is, I clamp C to be false. Okay, so, and then I just randomly put values. Assume these are all Booleans, or assume 1, 0, 0, 1, whatever. Okay, now I start resampling. Okay, now I just need to show you how to resample one variable, and then it's just the same thing again and again. Okay, and then as to when did it mix, I have basically, you wait for a while and then assume it's mixed and then start counting, essentially. Okay, so suppose I actually have this in this network. Suppose I actually have one potential on A not A. Remember I said that you can have clicks as well as subclicks. Any click, and a single variable is also a click. So there is already A being true is 2 probability, not A being false is probability, not the potential 2, and A being false is potential 1, without knowing anything else. And then I also have a deal between A and B and a deal between A and C. This is a third example of Markov network, so at least you'll see more of them this way. Okay, so I gave you these as the potentials, let's say. I'm writing the potentials in the normal form, not the exponentiated form right now, because once you understand this, you can do the other one too. Okay, so all I need to do is, so I need to resample, and let's assume that I already know that's in the current sample, so I need to resample A given B and C, because B and C are my Markov blanket. Now I already know C is false. That means this doesn't make any sense to me. I can remove this part. For this computation, C is already false. It's evidence. And also, so it was clamped to be false. It will always be false. In the current example, let's assume B is also false. Right? Remember, in the current state, you are always sampling given the current state. You started by initializing. In the initialization, you happen to have put B equal to false. So then this is also gone. Okay, then the distribution of A, B, and C is just in terms of these 3 factors. You do your normal factor multiplication. Okay, and then that way you can get A is 25.8, B and not A is 0.8. Okay, now you convert that into probability, 25.8 by 25.8 plus 0.8 and 0.8 by 0.8 plus 25.8. This is the probability distribution. So if B is false and C is also false, A is going to be true with 0.97 probability, false with 0.03 probability. So you get your shiny coin, which comes heads 0.97 probability, tails 0.03 probability. Actually toss it. That's very important. That is the only part that is required. Okay, so you computed the sampling distribution, then you actually pick the value of A from that distribution. You sample from that distribution. So clearly there's an extremely high chance that you will say that A is true, but there's a small chance that you will say A is false. Whatever the task tells you, that's what you will put as A's value. The moment you did it, now you are in a new state. Now you pick somebody else to sample. That's Markov chain Monte Carlo with Gibbs sampling. The Gibbs sampling basically takes just the neighbors. Basically, actually what Gibbs sampling says is sample a variable given everybody else in the network. That's what Gibbs sampling says. Now it turns out that sampling A given everybody in the network is the same as sampling A given just B and C in the network. That is the structure of Markov networks. Those are the 2 steps that happened. So in fact, what happened here is like a series of approximations. So there is this whole area called metropolitan Hastings algorithms. A special case of those is Gibbs sampling, which is a sample given everybody else, which gets instantiated to just sample given Markov blanket for graphical models. Gibbs sampling winds up being actually valid even if you don't have Markov blanket. I'm sorry, even if you don't have a graphical model. You just know that you have a whole bunch of variables and they have some sort of a connection. I didn't even bother writing any distribution as a, any graphical model for it. It's a much more general idea. When you use it here, you actually can use the Markov blanket information. Yes?
I must have missed something. When do we update the potentials? I mean, we got a new sampling distribution, sure, but what happens to A and not A in the top right?
Okay, somebody answer that question. What are we doing right now? What is this? Is this inference or learning? Is this inference or learning? What are we doing right now? It's inference. During inference, you don't touch these guys.
We don't care.
They don't, no, not they don't care. This is the knowledge about the network. Inference is a pure deductive task. This is the MDP part of Bayes networks. Okay? The pure learning is the pure learning. EM, something like EM is like RL, which does inference learning. Okay, it's a good question, but I was hoping that you are keeping track. We are only doing inference here. So you'll never touch these guys. You assume these are given. The tricky thing is, even though these are given, so in some sense, for this network, given these things, I could have just done what I did here. What I did in the very first slide, which is multiply all those guys, write these things, and then get P D naught C probability and P naught C probability by just marginalizing. You'd get a number. That's it. It's there. The reason you're doing sampling is because doing it this way, sometimes there isn't enough memory to hold the entire distribution. It's just too costly a way to compute that probability. Okay. So it's important to understand that this is what we are doing is here is inference, and you don't touch the potentials. During the learning, actually what happens, in EM you already know that during the learning, given the current potentials, you do inference. Given the current values, you do inference. And using the inference, you then rechange the potentials. Using the changed potentials, you do the learning again. That happens there. Okay, that only happened in the context of EM, in the context of incomplete data for Bayes networks. Unfortunately, it will also happen for the context of complete data for Markov networks. So the wish that you are asking for is going to come right next slide, because then you will essentially, every step, you'd have to take the current potentials to decide, do some part of inference and then change them for the next step. But this is a pure inference scenario. Here you don't change the parameters at all. You're just using the parameters. And that can be very costly. Remember that when you come to RL, it looks like MDP is child's play. But MDP was pretty hard. And what is mind-boggling is that after a while, you'll actually start trying to do MDP, which is supposedly child's play, using RL, which is a harder problem. And that is like variational inference. Okay, you're kind of throwing in a learning step, even though all you needed to do was to do pure inference. Okay. So anyway, so in this case, computing this distribution is what you need to do, and it's very obvious how to do it. It just depends on the Markov blanket. And just in case you're interested, here is one more step. Here now I'm going to resample the probability of B. Having computed that, I'm now going to resample the probability of B. Now, once I'm resampling the probability of B, resampling the value of B, its Markov blanket is just A and D. Okay, and it turns out in this particular case that I'll assume that unlike A, which had also a potential just on its value, B didn't have it. notice that that's possible. If you think that, whether A is true or false is not completely captured by just its interactions with B and C, but there is something intrinsic about itself, left to itself. Even without knowing anything about B and C, it has a more like, there is some affinity to become positive versus negative, and you want to capture that. That's when you do an extra potential like that. Okay, but here I'm assuming, I guess by not having given a potential for B, I'm assuming B basically lives based on its interactions with A and D. Okay, so, and once again, I would know the AB potential, which was the same as before, 154.3.2, 154.3.2. It didn't change, that's the point. Okay, and then the BD potential, which I did not show you, but it just happens to, I assume that it's like 1221. Now, once again, since in the previous state, presumably, I sampled with 0.97, 0.03 probability. Okay, you're not surprised to hear that I actually got A to be true. I could have gotten A to be false. In this case, I just got A to be true. Okay, and so now because A is true, the not A column can be ignored. And similarly, I'll assume that in the initial configuration, D hasn't changed in the last iteration. It was set in the previous iteration. So let's assume D was false in the previous iteration. So it still remained false because the last iteration you only changed A. Okay, so let's assume that was not D, and so D was false there, so that is gone. So once again, you multiply these and normalize, you'll get B not B to be 1 and 8.6. Now, the normalized is 0.11 and 0.89. So what this shows is B is much more likely to be negative, false than true. However, you can't just assume not B is true. Okay, it's only probabilistic knowledge. So you get your shiny coin, set its heads probability to be 0.11, toss it. It's more likely to come tails, but sometimes it can still come heads. That's Markov chain Monte Carlo on this. With Gibbs sampling. Okay, I went through this in so much detail basically because once again in the LDA the only thing we look at is collapsed Gibbs sampling, which is a fancy name for first get rid of the continuous variable. When you remove the continuous variable, there is more connections between the other variables, but they'll all be discrete, and then you just do Gibbs sampling on that. Okay, that's about the inference for Markov nets. The last thing I'm going to do, I guess I'm not going to get to relational models after all. The last thing I'm going to do is just show you that learning is hard. Okay, and so think of an extremely simple Markov network, ABC, with no directions. Okay, then it turns out that if you think and assume this is just basically in terms of there's a potential on AB and there's a potential on BC. Let's assume that's the only thing that's there. There's no separate potential on A or B or C separately. Okay, so I would have written this as if basically the log of the PABC is log of phi1 plus log of phi2 minus log of Z, which is the sum. Remember, because that is dividing everybody. The bad part about Z is pretty ugly. It is sum of products. Logs don't like them at all. Right? When was the last time you saw a sum of products in learning? EM. Because when there is a incomplete data, in essence you have to assume that what you are seeing is marginalizing the missing variable. To marginalize the missing variable, you need to sum over it being positive and it being negative. Okay, then the likelihood function will have sigma over products, and there's a log on top. You're dead. That's when you wind up doing normal gradient descent. Okay, not surprisingly, this is the same exact problem that comes up here. The only huge saving grace is that it can be shown that that this is the likelihood, right? this is basically going to be my likelihood, and it can be shown that the likelihood is going to be, you know, well, I mean, I guess you want to call it convex, you want to call it concave or convex upwards. It will only have one single optimum, which means that gradient descent will find the optimum. Gradient ascent will find the optimum. For EM, even that is not guaranteed because it can have multiple optimums. There can be multimodal, likelihood, and so you will just get stuck in whatever is the closest that you get to. Okay, so it is unimodal. However, it turns out that taking partial derivatives on this, essentially you don't get any closed form solution. Okay, and what's more interesting is, I'm sort of skipping over the finer details, but what's more interesting is that the partial derivative winds up basically requiring you to take expected values over features. To get the expected value, you are essentially using the current state of the network and doing inference. And using that, you change all the values. So you use the current values of the potentials, the current initialized values of the potentials, to figure out how much are you expecting to see based on the network configuration, and how much did you actually see based on the data. And you take the difference between them to decide the direction to move. And when you move, what are you moving? You are moving the potentials. So that next time around, you expect a different value for the feature. And if it's still different from what you're seeing in the data, you still move. Okay, so it turns out that this is expectation with respect to data. This is expectation with respect to the network. Okay, expectation with respect to the data is just, add up the number of times this happens to be true, divided by the total number of instances. Expectation with respect to the network, that's inference. You compute the posterior. When you compute the posterior, you also get the mean. You do this for a living in EM. But it's like painful to do it even when you have complete data. So which is why, essentially, as I said, so essentially this is another way of looking at it. It's like you're taking counts from the data and then subtracting the expected counts that you were expecting to see given the current valuation of the network, and then move the current weights of the network in the direction, in the right direction. Okay, so this is the gradient, and it requires inference at each step, and so it's going to be quite slow. The learning part will now require inference, and that inference part can use Gibbs sampling, for example. Okay. In fact, one of the neat things that I may not have said at the EM case is just like so that, remember, in the EM you need, you are computing the expected value, and then you're doing also maximization, expectation maximization. The expectation could be, should you use exact methods for inference or approximate method for inference? It turns out you can use approximate methods for inference. This, if it makes me remember, and I don't know whether any of you will remember, an interesting step we did for policy iteration. Where in policy iteration, you take the current policy, compute its true value, based on that compute the next policy, compute its true value, then based on that compute the next policy. Except we asked ourselves, do I really need to know exact value of this policy? What if I just approximate the value of this policy by running the value iteration algorithm without the maximization step a few times? I'll just give you approximately better understanding of this policy's value. Then use that to do the next value update. Do you remember this? Okay, so that way you did not have to do exact linear equation solution in the policy iteration. The same thing here. So, I can always compute this expected value without having to do the exact inference. I can just do some Gibbs sampling for a while. And then when I did the Gibbs sampling, then I can just count, the sample that I see. Remember, the whole point of Gibbs sampling is you let the thing settle down and then count the number of times, the configuration happened to be true in the last 10,000. Okay, so then this is the real data you saw. This is the pseudo data that the network would be willing to produce if you do this MCMC. So then it will become counts with respect to real data minus counts with respect to the pseudo data that the network will produce. But still, it's pretty painful because now you're doing Gibbs sampling, on a big network. Okay, you can do this. People do this, but if you read the entire, you read the Markov networks literature, this is where essentially, do any of you remember this term? Did any of you read the Chuck Norris things about Jeff Hinton? There is there's a joke on the contrastive divergence too, actually. But anyway, the point is that since the real objective, which is likelihood, is hard to optimize, I'll optimize something else which is easier to optimize and hope that both these functions will have the maxima at the same time. Now notice that idea in and of itself is not a stupid idea. In fact, you don't actually maximize likelihood, you maximize the log likelihood, because log likelihood is easier to maximize. However, there's a nice theorem which says that log likelihood will be having the optimum at the same place the original likelihood has, because log is a monotonic function. Okay, you did change the optimization once. Okay, it's just that you changed it much more carefully there. Now I'm just going to change it to all sorts of different things, such as, for example, pseudo likelihood, which is compute the likelihood of each possible data instance just using the Markov blanket. Notice now then, so if I just use the Markov blanket, that means I'm using the current, basically then I don't need to do the full Gibbs sampling essentially. I just have the neighbors, I just do resample with respect to that. Okay, and it turns out that learning would not require inference at each step. Another idea is called contrastive divergence that I'm not going to talk about. Okay, however, this is where the Pandora's box of finding other objective functions to optimize, because the real one is too hard to optimize, starts. And once you start it, it's a slippery slope. Okay, so a lot of work, for example, in quote unquote deep learning architectures. Now, what are deep learning architectures? Essentially, they are, mostly Bayes Markov networks over Boolean variables, where the conditional probability distributions are. Let me actually see if I have a picture here. Yeah, these are actually, there you go. There you go. The conditional. These are, by the way, these are happily copied from Hinton's Coursera course on deep belief networks. It's very useful to. He's the man who did this stuff, and one of the points is, so this is how a deep belief network would look. Okay, and what is a deep belief network? Essentially, it is this guy is a node and it has a bunch of parents. That's Bayes network. What's the big deal about it? Right? The only difference is I will assume that the conditional of I given its parents is writable as a sigmoid function. So it is, Hinton came here basically from neural network community. In neural networks, you have a threshold and you sum the values of your parents, you threshold it, and if it's greater than, the sum is greater than some threshold, the weighted sum of the values of the parents, you threshold it. If the sum is greater than the threshold, you put yourself to be 1, otherwise you put yourself to 0. So in essence, it's a step function. And there are no probabilistic semantics for neural networks. What deep belief networks do is essentially provide probabilistic semantics for the same idea of thresholding. Okay, so while that is a threshold function, that is a sigmoid function. Okay, it's nice and continuous, and it can be differentiated with at any place, and you can also think of this as a probability distribution. Okay, so what I'm going to say is normally given a Bayes network like this, any arbitrary conditional probability distribution can be given for I given the other variables, any arbitrary one. But I'm going to say that my distribution would have a sigmoid property. So that's a parameterized distribution. It's like saying my distribution will be noisy R. You see what I'm saying? And then in the case of sigmoid distribution, then basically it sort of looks like this function here. And the good thing is the number of parameters in Bayes networks is exponential in the number of parents. Remember that, right? Okay, that's why we like noisy R, because noisy R says the number of independent parameters are only polynomial in the number of parents, and the rest I'll just compute based on the parameterization. And the same thing happened here. Even though in general there should be exponential number of parameters to specify here, since I'm saying the form of the distribution is a sigmoid function, form of the distribution is sigmoid function, I only need linear number of numbers. A for us, because we now have much fewer parameters to learn. So that way it looks as if deep belief networks are easier than normal Bayes networks. But what's interesting is, in theory, Bayes networks can be of arbitrary depth. They have to be just acyclic, but they can be of arbitrary depth. But in practice, mostly you see 2-3 level Bayes networks, because it becomes hard to actually train them, hard to find the do EM sort of things. Now, one of the interesting things if you think of this as essentially a probabilistic version of the neural network, remember that neural network can be like deep in the sense you have an input layer, huge number of layers, and then output layer, right? So, and that is called a Bayes network. As a Bayes network of the comparable depth, this is much nicer, because each conditional distribution is a very highly parameterized sigmoid distribution. Okay. However, are you likely to get a complete data or incomplete data for training this guy? So I have a multi-layer Bayes network. I have inputs, I have outputs, and I have middle layers. Am I likely to get complete or incomplete data for training this? I'm talking to the walls at this point. Incomplete. Because you will know at most the input and the output. The middle layers are made up. You won't know the middle layers. That's the hard part. So you need to do EM. You need to do EM on this large, deep network. And in some sense, theoretically, this should be doable. It turns out that in practice, you can't do it. The EM algorithms won't work very well in practice for particularly deep networks, even with this kind of simplified parameterization. So what Jeff Hinton spent his lifetime doing, essentially, is finding engineering solutions, okay, that make the training feasible. And he would do anything. So, I mean, this is just, my way of looking at his work. A pure statistician would be very careful about changing the optimization function midstream. Okay, Hinton would say, look, you have nowhere to go. You are if you basically, the algorithms that you have won't work. So the optimization functions that you're trying to optimize, you can't optimize. So find things that will work. And so he developed a bunch of interesting techniques where basically he would wind up, all those techniques can be seen as either changing the optimization functions or changing the gradient ascent to be made easier. Oftentimes the gradient ascent winds up requiring doing inference, and he will tell you some way of getting away from doing inference. Okay, so much of the theory of deep belief networks is very much within your reach right now. Okay, what you need to see them as is, in essence, so it's like Archimedes saying that I figured out the whole notion of the way fulcrums work. So, you You need to lift the universe. I know how to lift the universe. Just give me a fulcrum point and a long enough stick, I'll lift it. Okay, that's more or less where we are going to stop when we understand, because the fulcrum idea works for basically small, weights pretty easily. But for large weights, you still use the same idea, but you need to figure out various kinds of interesting things. Okay, that engineering aspects become very important in training large-scale Bayesian networks. And one of the things that become important for them is, essentially, can you compute the sampling distribution? The stuff that you took as sort of a headache here. What's the big deal? It's 0.97, 0.03. Should I really have to go through all these steps to get this distribution when I'm tossing the coin anyway? Why not just take a random coin and toss? You have to ask yourself that. If in the end anyway you're going to toss the coin, how does it matter whether you got the right coin or the wrong coin? Well, it turns out the difference between getting the right versus wrong is the difference between asymptotic proof that you will converge and no proof whatsoever. Okay, and many a time he finds that getting these, in deep learning stuff, they find that getting these, none of them even touch variational inference. None of them touch exact inference. They'll all do essentially these sampling-based inferences. Turns out even sampling-based inferences become quite complex. Okay, and there are all sorts of interesting issues that you need to figure out as to how do you get a consistent distribution. Even if you don't get the real distribution, if you get another distribution that approximates this, then you can ask questions such as the bias of that distribution, is that a consistent estimate, and all that fun stuff. Okay, so I'm going to stop here. Basically, we talked about the fact that Markov networks exist, the fact that they have nice semantics, and that they have nice connections to Bayes networks in terms of independence assertions, and that you can talk about generalizing inference algorithms that work for Bayes networks to Markov networks. In fact, it's the opposite. The engineering systems for Bayes network inference just use Markov network inference, because that's a harder problem, and if you know already how to do it, this other one is just free. Okay, and then we also talked about the fact that that learning is possible in Markov networks, and then B, that the learning actually is harder in Markov networks than Bayes networks, because even there is no simple case anymore. Every case requires gradient ascent, and not only that, even the gradients themselves wind up requiring you to do inference. To get the gradient, you need to inference. So again, just as I said, why must you, if we are anyway going to toss the coin, must we kill ourselves trying to get the right distribution for the tossing the coin? And the same question can be asked, if I'm anyway going to do little steps, all the gradient ascent is doing is telling me do little step in a particular direction. Must I really get the right gradient? I mean, the fact that, the right gradient is this. What if I just make up only this part? Or make up this part minus some 15. I'll give me a number. I can make a step. How bad can it be? Now, the interesting thing, it turns out, is that for one-dimensional, low-dimensional cases, it doesn't make a big difference. Especially for a one-dimensional case, because in a one-dimensional case, the gradient essentially, all that matters is the magnitude of the step, because the direction is just one direction. Okay, in multi-dimensional cases, getting the gradient wrong means you're getting the vector wrong. Okay, so if the goal is that side, and if my gradient is saying you should make 15-inch step, and I made a 14-inch step, no big deal. Maybe I'll still get to the goal. If the goal is in a three-dimensional space, and my gradient says that I should make a 15-inch step in this direction, and I made a 14-inch step in that direction, I'm dead. There's much lower chance that I'll actually get to the goal. So again, it's important to understand why getting the gradient is so important, because in multi-dimensional cases, essentially the direction matters, and when you are not getting the right numbers, you're changing the direction. Because you change the magnitude of the coefficients of a vector, it changes its direction. Now you're going off in a different direction in the multi-dimensional space. Okay, so, and bringing that up was useful, and also the fact that in many cases, when going gets tough, people change the optimization function and hope for the best. Okay, basically, when you change the optimization function, here is a pseudo likelihood function, and it does not require inference at each step, so it is easy to do. It's sort of like me saying, why not, why must I compute this? Why not just take this and minus 10, some random number I make up? Okay, that way I don't have to do inference. The pseudo likelihood function says, whatever arbitrary thing you are doing, which without doing inference, can be shown to be the right thing to do if what you're optimizing is this. Okay, in fact, this is actually a very interesting point. Much of this whole entire area of information retrieval, for example, and even in machine learning, there is a difference between statistical machine learning and machine learning. Okay, machine learning, anything works, that's fine. So, for example, take something like k-means. Why does it work? No, it works. I do it, it works. Okay, and what statisticians say is, when is k-means the right thing to do? They would say that if your data was generated by a mixture of Gaussians, then under those cases, a version of k-means called soft k-means actually is the probably right thing to do. Then, of course, if your data is not generated by, most of the time when you do k-means, do you actually ask yourself, has my data been generated by a mixture of Gaussians? No, not at all. But at least you know when you will go wrong. If the generative model didn't work, then that is the time when you would go wrong. In some sense, knowing, not just simplifying your work, but telling yourself, asking yourself exactly under what conditions is this wrong thing the right thing to do, is a very useful insight. Much of statistical learning really is about that, compared to non-statistical learning. Statistical learning, people want to know under what condition was this the right thing to do. So, you can say that the pseudo likelihood based gradient descent, what we really hate is this business of dealing with the inference. I'll remove the inference. And then they're telling you that if you are optimizing this function, then what you just did is the right thing to do. Then I can ask yourself, then you have a better chance of understanding when is this algorithm likely to work or not likely to work. Okay. By the way, so I mentioned, the last thing I want to say is I mentioned that Markov random fields have been around, in vision for quite a long time, and they use all these features. The features for them would be edges, etc., which will be defined in terms of the individual pixel intensities. Okay. Let's say. So then the question is, they compute the the feature weights using learning, but they do pseudo likelihood maximization, and there is no actual guarantee that it will work right, especially when there are long inference chains. It won't work. But in vision applications, the errors are not going to come up as much. By the way, this business of long inference chains reminds me that many of you know about fuzzy logic. At least I heard about fuzzy logic. So read the little description of fuzzy logic and its connection to probabilistic logic, which is Bayes networks and so on. Okay, fuzzy logic makes life much simpler. It acts as if you can always compute the truth degree of any arbitrary function over the random the variables, okay, just in terms of their individual truths. Whereas probability requires the entire joint distribution and marginalization, etc., etc. And there is a raging debate for a while, now it's no longer there, as to, since fuzzy logic works so well and Japanese are making, for a while at that time, Japanese were making washing machines which use fuzzy logic. Okay, just as the vision people are making Markov random fields which use, pseudo likelihood. It works. How come it's wrong? Well, it could work because you are not doing, for example, in this case, long chains of inference. And the same thing is true for fuzzy logic. It turns out if you actually wind up doing long chains of inference, fuzzy logic basically dies. That chapter at the end of the probability chapter in Russell and Norvig, which talks about all various other approaches to probabilistic reasoning that people have tried, including fuzzy logic, including certainty factors and so on. And they seem to work sometimes. And there is this great temptation that you don't need to know anywhere near the amount of theory to understand them. But they'll all die eventually, at certain cases. Okay, so anyway, so in the case of vision, actually they use the simpler objective function and they seem to get by fine. Okay, and then the contrastive divergence, which I didn't mention, is actually used a lot in the deep learning. If you're interested, you can read that. So that's the connection. So you just change what you're optimizing and sort of try to make an intuitive argument that why don't we optimize that? Isn't it a reasonable thing to optimize? And then now if you agree with me, then I'll give you a nice, easy gradient computation. Okay, we'll stop here. Thanks. Eat more donuts, please.